Hello, everyone. My name is Sasha Zelanovic. I work at Red Hat AI. I've been one of the co-hosts for these office hours. 56th right now. It's hard to believe, honestly, that we've done 56 sessions. I'm here with Michael Goin, who's been here for every single session but one. Michael is a senior principal engineer at Red Hat AI and also a vLLM core maintainer. I always tell people, I don't know if Michael loves this, but I always tell people there's no vLLM or inference in general question that Michael doesn't know the answer to. Excited to hear from him and feel free to ask any questions. So we can take questions in the chat anytime. You can raise your hand and speak up, or also we'll have a Q&A, dedicated Q&A time towards the end of the hour. We are cool to stay longer. If you want to dig into something deeper after the hour, we're very happy to stay. We always just book the next hour and we can stay as long as you guys want. I'm excited for today's few topics, actually. This is the first time we're doing 3 different topics. So agenda is definitely getting busy. Our special topic today. So typically, if you're new to these office hours, we'll do a quick update, project update. So what's new in the vLLM community in the last 2 weeks since the last Thursday session. Michael will go through that. He'll share some cool blogs and also go deeper into the actual release and tell you what's new. And then we go into our special topic, and those usually take between 20 and 30 minutes. Today's special topic is about GuideLLM, which is an inference benchmarking tool. We'll talk about benchmarking reasoning, tool calling, and agentic traces. This is all new in GuideLLM v0.7. And then for 2 of the special topics, really excited. These are something new we're doing. They're about 5 minutes each. We'll be talking about running Codex and Claude code CLIs with vLLM and open source models. And then we'll get a quick Speculators project update. So what's new there, some of the new models. If you ever want to speak at these office hours, you can just speak, or you can also let me know through vLLM Slack. So slack.vllm.ai, you can find me and Michael there. If you want to just get dedicated time, that's not just raising your hand and speaking, we would love to hear from you. We're always looking for new topics. Also, if you think that you want to learn something that maybe you don't know and you don't want to speak on, but somebody might, also just let me know. We can always figure those things out. So let me just go to the next slide. So for the upcoming office hour sessions, we have one planned for in 2 weeks. That's about vLLM Omni. So we'll share what's new in the multimodal vLLM space, so update, and we'll show you some pretty cool demos. We're also working to schedule a session, an update session on semantic routing. But again, if you guys want to hear something, if you want to learn something, we have, I believe, 12, maybe more core committers, vLLM core committers in the Red Hat AI team. And we work with a lot of the community members from NVIDIA, from Meta, Hugging Face, Mistral, the AMD, the list goes on, Intel. So if there's ever a topic that you want to dig into, you can Slack me, you can send me a message. We'll make it happen, I promise. All right, Michael, I'm going. Oh, this is being recorded. We put all of our sessions on YouTube. Also, slides are public. They're linked into our YouTube descriptions. Michael's shared them already in chat. You can totally follow along if you want. And with that, Michael, I'm going to pass it over to you.
Yeah, well done, Sasha. It's like you've been doing this for a while. Yeah, hey everyone, glad to be back and give you an update on vLLM and what's new in the past 2 weeks. We've got a few big model releases. I'm going to focus on Qwen 3.8 because that's the latest, trillion plus parameter model. We also have some blogs on decode context parallelism, how that's been added and optimized in vLLM where it's useful. Adaptive verification, which is a really important part of DSpark as an optimized speculative decoding method that we're excited about adding that capability in vLLM generally for speculative decoding. Tell you a bit about the vLLM conference, and then the latest 0.27 release that happened over the past 2 weeks. So let's go ahead and get started. If you're not familiar with vLLM, it's the most popular open source inference engine for large language models. It's part of the Apache, it's a part of the PyTorch Foundation, Apache 2.0, very vibrant GitHub community and project with over close to 90,000 GitHub stars, thousands of contributors landing code in the project every day. We have a huge amount of PRs and issues thanks to the vibrant community and also everyone's AI agents. So we're very much having fun trying to scale up and deal with all the load in a very active project like this, and love the community that powers it ultimately. vLLM, of course, runs your favorite models performantly on NVIDIA, but also several other dozen plus hardware backends, all the various hardware accelerators, especially on the data center side, run and target vLLM as the efficient abstraction for running the state-of-the-art large language models of the day. And vLLM as a community goes beyond the inference server itself. We have many projects under the ecosystem like vLLM Omni, compressors. Today you'll be introduced to Speculators, GuideLLM, Agentic API, and learn more about those sub-projects or projects in the overall community. So yeah, let's go ahead and get into what's new. So as you hopefully knew, Qwen released their Frontier class model last week or so. And we have two updates there. Obviously, we support the model on day 0. Everyone wants to run the biggest 2.4 trillion parameter model. And we also had a blog shortly before that with really from NVIDIA on a lot of their work they pushed on Qwen 3.5, which is, of course, is a smaller, around 400 billion parameter MOE, but thankfully has, and maybe conveniently, has a very similar architecture to Qwen 3.8. So a lot of those optimizations that went into that work to get 25K tokens per second per GPU on a Grace Blackwell GB200 system also apply to this trillion parameter scale version of the Qwen 3.x series. Yeah, if you're curious in how and what it took essentially to run this architecture efficiently on vLLM with the latest NVIDIA hardware, there's a lot of goodies in there. And hopefully you can learn a bit more about as well how to efficiently serve it in a disaggregated fashion with separate prefill and decode workers scaling up on a long agentic task. So that's that model release. As I mentioned before, we have decode context parallelism. This has been a feature in vLLM for a long time, actually originally contributed by the Moonshot AI Kimi team for, I think, Kimi K2 when that came out. And yeah, we've been developing and generalizing this new type of parallelism for a while now. So it doesn't just apply for MLA models like DeepSeek or Kimi, but also to group query attention models and most types of attention in vLLM. Ultimately, this is a way of parallelism specifically for the attention layers, and particularly the decode part of attention, that, when you only have a few attention heads and you do tensor parallelism, usually you do that over the attention heads. So if you only have one attention head for MLA or four for aggressive GQA, you need to start replicating attention heads across tensor parallel ranks. And this means you have to start replicating KV cache between ranks, losing storage that you could use for storing more tokens, longer context, and thus a higher batch size when you're serving longer context requests. So for a model that uses MLA, where you're running TP8, running it across 8 GPUs on a node, switching it to use decode context parallelism means that we now have 8 times the space for KV cache while still getting the low latency performance that you want from a TP optimized deployment. Yeah, so if a lot of those things were confusing and I threw a lot of words and terminology, I recommend reading the blog. It'll guide you into what this type of parallelism means. We're actively working on, we have prefill context parallelism or PCP integrated in vLLM and are working on expanding it in a general way as well. This helps more of the sort of prefill side of the equation, speeding that up. But yeah, learn about this stuff if you're interested, especially in running these large models on large number of GPUs. It's a really important throughput optimization. Next, I mentioned adaptive verification is finally in vLLM. This is a key concept introduced by DeepSeek in the DSpark paper. Essentially, these figures are a little bit small. In traditional speculative decoding, you define how many tokens you want to draft each forward pass. You want the speculator to produce maybe 6 or 8 tokens that it's going to speculate on. And you run all those speculative tokens through the verifier, which is your target model. And then it tells you what tokens that it wouldn't predict because spec decoding is a lossless acceleration method. Now, in this case, these blocks, each one being a token, are colored where darker means we're less confident that those tokens that we drafted are something that the model would actually verify. And DSpark has this confidence head, which gives you this level of confidence. And with adaptive verification, we can actually choose to prune out the draft tokens that we have low confidence, thus running a smaller batch size through the verifier and ultimately wasting less compute, verifying tokens that we are pretty sure that the verifier would not accept under any case. So here in this benchmark, we have all of these sort of these yellow to red lines are running a DSpark model with varying levels of K or number of tokens it's drafting and predicting. And obviously, as we increase the number, we get better batch size 1 latency, or the C1 is concurrent C1, better interactivity. But as we go to higher levels of concurrency, scaling up this Pareto frontier, this darkest red line is K7, which is predicting or drafting 7 tokens every forward pass for every request. And adaptive verification means that we start pruning the requests that have, pruning tokens from requests that have less high quality predictions and are ultimately able to both give like the best low latency batch size 1 throughput, where we have tons of compute budget to spend on spec decoding, and scaling back the number of speculative tokens we do for each request as we get to that optimal, or we get enough compute from the concurrency of 256 users at once. And this green line is no spec decoding. It makes spec decoding a no-brainer and a clear improvement automatically for you, where you don't need to start tuning this K parameter for your specific deployment, depending on what level of load you're working at. So this is something that's obviously introduced with DSpark, but doesn't necessarily rely on anything inherently special in DSpark. We can apply this to many other speculative methods. And so we're really excited about adding this heuristic, this adaptive verification concept generally in vLLM for spec decoding. So we can make spec decoding something that you want to run on any model. If vLLM sees that there's extra compute available because it's in a low batch size regime, we might as well just start passing those tokens through the model if we can have high confidence that those tokens are going to be something the verifier will accept. So a lot of things there. Again, highly recommend reading the blog. It's a great introduction to the fundamentals and why this kind of optimization is important. So those are the blogs. Now I want to cover the vLLM conference. If you're going to be in the Bay Area next week, Tuesday, Wednesday, I will be there as well as many others in the vLLM community. TJ is going to be there as well. And yeah, we have tons of talks from tons of companies, Red Hat, obviously us, Infract, NVIDIA, AMD, Intel, Google, PyTorch, Embedded LLM, Hugging Face. It's going to be a packed day. And if anyone wants to get a free ticket, I have maybe a few extra codes to let people in if you're in the Bay Area that week. So yeah, and lastly, I'm going to cover what's new in the latest vLLM release. This was a pretty big release. We had over 561 commits within 2 weeks, which is a lot. 242 contributors, 64 of those brand new first-time landing code in the project, which is really cool to see. This was the first release where we landed Kimi K3 stable within the release. So that's fully supported within this release. We are still pushing a ton on DeepSeek v4 and also GLM 5.2 performance. Lots of optimizations there, particularly pushing on sequence parallelism and compatibility with other different types of parallelism. We've also been working a lot on Model Runner V. So now it's starting to be supported for non-generative workloads. So supporting pooling models, encoder-only attention, and starting to cover the more longer tail of features into Model Runner V2. So we can hopefully deprecate V1 within a short timeline here. Also, we're working a lot on Flash Attention V4, adding FP8 KV cache support there. So that runs through that backend on Blackwell GPUs. We're also tuning performance for weird head dims like Gemma 4. And we've landed the start of our JIT warm-up infrastructure, which is actually more general than FA4's cell-based JIT. We've also landed this for Triton and tiling other JIT languages we use in vLLM. But ultimately, this is infrastructure to make sure that we JIT and warm up all of the kernels that you're going to see at runtime during the startup of vLLM. So hopefully, once you're running vLLM and your endpoint is healthy, you don't need to worry about warming it up after that with then some production requests, and hopefully avoid jitting at runtime, which ultimately is going to cause a latency spike in your service, which we don't want you to have to worry about. Yeah, various optimizations for spec decoding, as well as some bug fixes with structured outputs and tool calling. Lots of various work on quantization, a good bit of improvements for TurboQuant, KV cache quantization. Happy to see work on KV cache compression there. Also within this release, we updated PyTorch 2.13, which is a big revision bump, but pretty smooth, I think. And we also landed our first support for the next generation of hardware, actually both from NVIDIA and AMD. So NVIDIA Rubin with SM107 landed initial support, with CUDA 13.4 being the first one that supports that. And then the ROCm GFX 1250, which is the MI450, I believe, is getting at the start of its support there. So very exciting to see the next generation of hardware coming online in open source. Yeah, lots of various kernel optimizations. AMD has been pushing a ton on ADER improvements and again, DeepSeek optimizations as well. We landed fault tolerance for DP plus EP with external load balancing and are making it easier to enable fault tolerance and manage it with a RESTful API, which is a nice way for expanding this feature for more types of deployments, not just requiring working through Ray or something like that. We've also been working on expanding the stability of pre-filled decode disaggregation for hybrid models. This has been MLA and SSM is obviously really important for K3 as we scale up there. So a lot of optimizations there as we get some larger deployments with large models like that. Great progress on the Rust front end. We've started adding support for the gRPC control plane rather than just the HTTP based one. So good to see the maturity there. And various bug fixes and feature rounding out in the server API. So that's all I'm going to cover on vLLM, and I'll hand it off to our first set of speakers, Francisco and Tun Jian.
Awesome. Thanks, Michael. Awesome presentation. I am going to share my screen. Hopefully it goes all right.
We trust you.
Yeah, hopefully. All right. Can folks see my screen? I think I see it, but just a thumbs up from somebody. Cool. Here I'm Francisco. I work at Red Hat, do computer stuff. And I'm here to talk with you today about this vLLM ecosystem project called Agentic API. I've had the pleasure of working with the embedded LLM folks, TJ in particular, for the last several months. And we're really excited to share that we finally got an MVP. And what the MVP is basically additional support for these agentic harnesses, particularly Claude Code and Codex on top of vLLM. And so I'll go into a second about what that means, but that's really what we're going to talk about in the next few minutes here. TJ, did you want to introduce yourself?
Oh yeah, hi. Yeah, I am TJ for short, my initials. I'm from embedded LLM. So basically we are working on the broken support on the vLLM repo and vLLM Omni as well. And now, because we want to bring further capability to vLLM, so we started this Agentic API together with Red Hat, like Francisco, because we wanted to keep the stateful logic outside of vLLM, to keep vLLM just a stateless inference engine. So that's why we have this Agentic API project. Yeah, and one of the contributor like Hao San is also here in the room with us as well. Yeah, but I'll pass back to Francisco. Yeah, he will be explaining about what we are working on. Yeah.
Awesome. Yeah, we're going to get to the point, running Codex and Claude Code with vLLM and open weight models, which we love, right? To start, agentic workloads need more than just token generation. Unfortunately, stateless generation is not enough anymore. It has written a really great blog post about this in their response API. They did this when they actually open sourced GPT-OSS. I invite you all to take a look at it and read it because it is really awesome. I have spent a year of my life on it, which is a long time. Maybe not proportionally because I'm old, it's still meaningful to me. But there are 4 key things that have to happen, which is 1, state management, as TJ mentioned, which is really just persisting like your previous churn, right? Historically, people just sent a big old blob of text. And now you don't necessarily have to send the biggest blob. You can send the marginal blob, which is basically the incremental text of an individual churn. And then tool execution. Now with the responses API, you support server-side tool execution and tool orchestration for coordinating multi-round loops, and then provider integrations. And the provider integrations are like web search providers or database clients. And these are the things that we built into Agentic API, which is built in Rust for real high scale. And so what does it look like? It's pretty simple, actually. You take your harness, Codex, Claude Code, or SDKs, and you connect it with vLLM Agentic API, our Rust server, and then you do some configuration, you declare which models you want to use, and then that's going to point to your vLLM instance, and then you're done. That sounds easy. Maybe it's not. The MVP, we just finished it this week, like I said, and wiring it up to both Codex and Claude Code, which is the demo I'll show in a minute. And we've just started to work with the LLMD community about actually turning this into broader stage agentic inference. And so there's a lot of really exciting work in the community that's happening, coordinating between these folks, whether it be to embedded LLM, IBM, Red Hat, Google. There's a lot of folks that are excited about this work. And so we're really excited about getting this stuff out here. It's still early, so apologies, there'll be some bumps, but we're working through it. Yeah. And so I'm going to show this demo. I have a live one, but rather than spend a whole bunch of time, I'm just going to show the recorded one because it's a little bit easier. But what's going to happen is the request is going to be pass through from the client, the harness. It's going to hit the Agentic API server. It's then going to do inference. And that inference is going to say, hey, do a web search tool call. And then it's going to actually go and execute it. And in this case, we used u.com, great provider. We like them. And it's going to refer that tool call result back into the inference engine so it can finish its churn. And it'll resume inference. As you see here, the final tokens will be generated and will be passed back and streamed into Codex. There's a whole bunch of other boring implementation details about what we do in this Agentic API server. And I invite you to check out the repo and the SIG channel. But suffice to say, it gets the thing done. So here, let me show you this very short demo. You're seeing the Agentic API server on the left, and on the right, you're actually seeing the response. So the first question is, what is GPT 5.6? Because this is a Qwen 3.8 model, it doesn't have a GPT 5.6 in the training data. And we said, don't use tools. So from memory, it says, hey, look, I don't know what's in there. I don't know what that is, but maybe that's something to do with the OpenAI. Then we prompted again to
the video is we can't see the words.
Oh, okay. It's a little bit hard to see. Let me see if I can. Is this better or is this too big?
Yes, it's better. Yeah.
Okay. So what you're seeing here on this last churn is now I ask it in the second turn to search the web and tell me about GPT 5.6. And what you can see on the left pane is the actual web search results where it queries it. And you can see some of the links there on the left. And the response is generated here on the right where it says, oh, GPT 5.6 appears to be OpenAI's latest model family, announced in August 2026. Now, I don't have, my example below shows, on my local environment shows both, but for the sake of time, I don't want it to go through a demo hell. But that's basically the idea of what we're doing here. There is a lot more emerging that are stateful properties about these APIs that are embedded in the harnesses, particularly memories and computer history. So these tools are increasingly stateful, and we're really excited in the Agentic API project to actually tackle those and make sure that vLLM has a really great user experience when using these harnesses with open weight models and open source software. Cool. Any questions? Awesome.
No, very
See everybody in Slack.
Thanks so much for sharing. Yeah, Rahul, do you want to take it away for speculators?
Yep, thank you. Hi, everyone. I'm Rahul Tuli. I'm a software engineer at Red Hat AI and a core maintainer of Speculators repository. I just wanted to drop in and give a quick lightning update on some of the cool stuff the Speculators team has been doing since the last time we were here. I think it was office hours number 51, if I'm not wrong. And a lot has shipped since then. If any one of you is interested in knowing more about speculators and speculative decoding, I highly recommend watching that. All right. So since the last time we were here, we've shipped 2 full releases, 0.6 and 0.7. 0.6 was all about algorithm coverage. We added quite a few algorithms there. We added P-EAGLE, a parallel eagle variant with conditional drop token sampling. And we also added multi-token prediction fine-tuning. So a lot of models now, especially the Qwens and the DeepSeek, have started shipping with their own native multi-token prediction head. MTP fine-tuning sort of helps you in the sense that instead of training a drafter from scratch, we can leverage the existing MTP head that the model providers give us, and you can fine-tune it on your own domain-specific data. And based on our internal benchmarks, it is pretty good. We highly recommend if you have a model that ships with its own MTP head, that you should try to fine-tune its MTP head as a drafter. And it's also the easiest algorithm to get started with. Other than that, we also added DFlash support and improved our multimodal dataset training and added sliding window attention for DFlash. With 0.7, while the release continued to expand our algorithm support, we also heavily focused on improving the training UX. We added DSpark, which is a new variant of DFlash. It essentially extends DFlash with a Markov logic-based head for intra-block token dependencies. amount. Plus, it also adds a per position confidence head, the one that Michael was talking about. And now you can train all of that on your own using the Speculators repository. In terms of the training UX, we switched to a config file first training CLI. So all the big training commands can now just go inside a YAML file, and the training command looks way simpler now. We expanded our loss library. We added DBase, which showed quite good acceptance rates based on our internal benchmarks. We also added PV loss, JSD, and a lot of fun stuff. So please check that out. Since our 0.7 release, Neon Optimizer has also been chosen as our default optimizer. We just saw that this optimizer leads to better convergence and also faster training. So check all that out. We also improved quite a bit on our tool call and multi-on policy response regeneration. A lot of these drafters essentially try to mimic the distribution of the verifiers. So if the drafter is trained on responses regenerated using that verifier, it's been seen to give better quality. It's been seen to give out a better quality output. Not the output, in the sense the acceptance rate is just higher. So try all that out. Then next, other than all the coding that we've been doing on Speculators, and we've also been keeping our GPUs quite busy. This past month, we released about 12 new Speculators on Hugging Face. The big one there being a Kimi K3 DSpark speculator. This speculator was trained using a multi-node setup, and we used the newly added Mooncake hidden state extraction backend to transfer the hidden states. Other than that, we also added quite a few speculators for model and GLM2. The acceptance rates, the acceptance rates here are just the average acceptance rates. But if you go to the model cards for each of these models, then you should have a lot more information. We've run extensive benchmarks, and you can also get the vLLM serve command directly from the model cards. So I highly recommend everyone to check that out. Now, our work didn't necessarily just end after the release. Since the release, we've been continuing to improve the repository. The Mooncake hidden state connector backend that I was talking about has been already merged into main, and now it's being packaged into its own package, HS connectors, and will be available on PyPy. We are also targeting to add more hidden state backends like quantized FP8 hidden state connectors, and all of that will go into this new package. We also improved the provenance for our training and eval flows. So every training and eval command now ships with text files and YAML files that sort of exactly show you how the training was run. And if you made any changes to the repository while you were training, it also shows you the git diff of what was done. So all runs are now reproducible quite easily. We also improved our response regeneration. So check that out as well. And then all of our loss functions now, they go through a single Triton kernel, which gave us quite a few memory benefits. So now training speculators take even less memory. We also took this opportunity to bolster our nightly testing to just keep in sync with vLLM a lot better than what we were doing before. With this, I would also like to call out that we maintain, if you're interested in contributing and just knowing more about the repository, we maintain a roadmap on GitHub, and we make sure it's up to date. So if you have any recommendations, any new features that you guys want to see, or are just interested in checking out what are we working on, please take a look at that roadmap. Other than that, I would highly recommend everyone who's interested to reach out to us on vLLM Slack in 6 spec decode channels and also speculators. Our team is very active there, and we're more than happy to answer any queries and help you along your journey. That's pretty much it from me. If there are any questions, you're more than welcome to ask. Otherwise, I'll just hand it off to Sam and Jared.
Could I ask a question?
Yes, please.
Yeah. Oh, we have more topics at the end. Sorry. So the question would be like, because I noticed that there are multiple DSpark weight for Kimi K3, And one of variant uses MLA attention backend. But from Red Hat, the one that Red Hat releases uses a Quint tree style GQA attention. Now, how should we pick the type of attention backend that, how we know it performs better?
That is a very good question. So the quick answer is, based on our internal research, we went with the Quint tree style attention for the first pass, but we are still running more ablations and a lot more comparisons, and all of that is also included in our roadmap.
Yeah,
I do not have a very good answer. Maybe Michael can add more.
I can say from the vLLM side, please stop making new types of attention in the speculators. Please continue to make Quen GQA style with sliding window attention. Yeah. Every time you make one of these new architectures, we have to add a new model architecture into vLLM. The MLA is like a very specific type. Also, you have to remember from the training side, in speculators, now you need to implement new architectures. How do you train MLA attention is different than how do you train GQA. So I think generally what we found is like changing the architecture to match the architecture of the target model doesn't really have any clear value. So it's better to come with a stable architecture for the drafter that just continue training that like same drafter architecture for different target models. Yeah. And then that makes it easier, I think, both from the training side and the inference side, because there's no real reason that they need to be connected. And then there's other things like sliding window attention on the drafter that make the drafter scale so much better as you go into long context, make the training easier and more generalizable, where if you start trying to replicate the target architecture in the drafter, that opens up a whole bundle of questions, especially once you start getting into target models that have hybrid architectures with Mamba and global attention and sliding window. Yeah. GQA with sliding window, Quen style we have no reason to believe that this isn't a good base to go off of.
Oh, wow. Thank you. Yeah, this is a very informative. Just another one small questions like how should we pick which layer of the hidden state we should get it from?
That is a very interesting question, and there is a lot of study going there on the optimal way for selecting which layer should we get the hidden states from. But for now, what we've seen, it really depends on the algorithm. For example, we tries to take hidden states from 3 different layers, some layers that are at the beginning of the model, some layers that are in the middle, and one of the layers that are towards the end of the model. And what we've seen is a lot of model providers, they have their own recipe. So it still varies quite a bit, but we haven't seen a lot of differences as of yet. And on the other end, if you're using DSpark, then we recommend using at least 5 layers. But a lot of these answers depend on internal experimentation and what is the domain that you're trying to train the drafter and verifier for. So a subjective answer, I don't know if I answered it very well, but that is what we've seen internally.
Thanks, Rahul.
Thanks.
I think it would be great to go to the GuideLLM, the special topic, so we can give those guys the appropriate time. But definitely, let's keep asking questions, and we're happy to stay until the end, longer than usual, and answer anything that comes up. All right, Sam, Jared, what's going on?
Hello, thank you.
There we go. Hey, everyone. Welcome to our presentation on GuideLLM 0.7 and beyond. I'm Samuel Monson. I'm a senior software engineer at Red Hat.
I'm Jared O'Connell, a software engineer at Red Hat.
Today, we're going to try to do a high-level overview of performance benchmarking in GuideLLM. We'll just start with some basic concepts for performance benchmarking. We'll reintroduce GuideLLM since I assume most people were not here at our last office hours over a year ago now. Then we'll go into some usage for GuideLLM. I think the big kind of main topics for 0.7 and looking forward is the agentic workload stuff and kind of the update beyond that. So let's just start with some high level, what is AI benchmarking? So generally, when we're talking about like performance benchmarking, we're looking really at we're looking mainly at the user experience of using an LLM. So you'll look at these kind of metrics that are the latencies and the throughput that the user is experiencing. So time to first token, for instance, is when you get back your first token, basically your first decode. And that's kind of the latency that the user is experiencing waiting for their request to come back. And then we have these like other metrics like intertoken latency, which is measuring the time between each token, kind of the responsiveness of the model. And then of course we want to know what our systems are doing in terms of like how many requests they can handle, like the overall throughputs and whatnot. So we have a lot of different metrics that we track to figure these things out. A lot of these do correlate to things you could track internally in vLLM, but the main difference here is that we're actually looking at the user perspective, so like the time to first token is not going to be really the same as what vLLM reports, because there's many layers in between that and what the user ends up actually seeing. So like I said, we've tracked different throughputs, we track statistical summaries of all these metrics, if we're airing requests, whatnot.
So we have to simulate a lot of different request patterns depending on what you would want to test and what bottlenecks you're looking for. So you can start with more user-driven closed-loop patterns like synchronous, which is just one request at a time, or concurrent, which is many concurrent one request at a time. Concurrent is good for finding like the throughput ceiling of your LLM server. We also have more realistic traffic-driven open loop scenarios like constant or Poisson, which more accurately tests real loads because requests arrive independently of server speed. Trace data sets, which are becoming very popular, are real recorded timings rather than mathematically generated ones. So they're very good for realistic timings. We have to support many different types of data sets, including many from Hugging Face, since that is the most common and popular source for data sets, as well as file-based data sets, which are stored locally. We also need to support generating synthetic data so that you don't need to have your own data set to run basic tests. We also need to support various types of data in those data sets, including simple chat, multi-turn chat, which we'll get into more later, where you keep talking into a conversation with an LLM. And those chats can have tool calling involved. And it may also involve subagents for when the server or when the LLM decides that the research needs to be offloaded to other agents.
So our solution to this is GuideLLM, and it's a tool designed to solve all these problems. We see it used for a variety of different use cases. You might use it like pre-deployment to conform. Say you have a bunch of models you've selected on accuracy. If you want to figure out which of those models best performs on the hardware you have, you can use it there. You can use it for capacity planning. Given your model and hardware, you can figure out exactly how much load your hardware can handle before you need to maybe scale beyond that. You can use it for maybe A/B testing. Maybe you're testing different speculator models, different performance tunables in vLLM. You can use it there. Or you could even be evaluating hardware given like keeping a model and figuring out which hardware you would perform best on and suit your needs the best. To accomplish this, we've built a layered concurrent architecture to allow us to distribute the load of testing an LLM across as much surface area as possible. We're using all of the different Python primitives that you can use for just distribution. This gives us some guarantees around accurate scheduling of requests.
Is it just Sam? I think it's just Sam, right?
Sam, I think you froze. I'll continue the slide while we wait for Sam to Sam, you dropped out there.
Yeah, can you hear me now?
Yes, the second half of the slide got dropped out.
Okay, yeah. So I was just saying that the concurrency design gives us these guarantees around accurate scheduling, minimal overhead, and helps with keeping runs deterministic from a performance perspective.
So GuideLLM is modular, open, and extensible. So if it doesn't support your current needs, it is likely that you might be able to contribute a portion or a new feature to help fit your use case. So for example, we have components for dataset processing, so you can add support for new types of datasets, like Mooncake was added recently, for example. We support various types of backends, which we'll get into later. We support various scheduling things, as discussed earlier, various constraints, like stopping after a certain amount of requests. We recently got a contribution on that for stopping after it detected the server became overloaded based off of the request timing. So that's very helpful for certain use cases. And we also support modular outputs, which can include machine readable ones like JSON, which is the default one that includes just about everything GuideLLM collects. But we also have the HTML output, which is being revamped right now, which we'll show later, which is not intended for the machine. It instead contains lots of graphs and other data to present it to you well. We support various backends, including the most popular one, which is the OpenAI HTTP backend, which supports the basic legacy completions API, the newer chat completions API, which supports chat templates, the responses API, which better supports more modern agentic features. We also support the real-time audio WebSocket API, as well as running vLLM within GuideLLM within the same process using its Python API. For that, we support the LLM API for batching and the async LLM engine API for streaming. We also recently got a community contribution for the LightLLM SDK. We're not going to get into the architecture too in depth today, but here is a visualization in case you're interested. So next is using GuideLLM. So here is a basic GuideLLM command. This is just a simple request that you can run even just on your local computer if you can run a model server. In this case, it is communicating with the OpenAI HTTP backend running locally on my computer on port 8000, running the Qwen 3-0.6b model, which is small enough to run locally. The profile is synchronous, which is just one request at a time, running one after the other. So it's very light, will likely not overwhelm your server. A good starting point because of that. And it only runs for 15 requests. So good starting test. For the data, it's synthetically generated, and it will generate 256 tokens to send to the server. And then we ask the server to reply with 256 tokens. Next, we have the demo. So this is a recording of that exact command running on my local laptop. It starts by loading all the libraries, and now it is starting up the processes. And because it is multiprocessing, someone asked what the benefit of synthetic data is, and I think the main benefit is that you don't need to have it. It's just a bunch of tokens that test the server. If you need more specific stuff, you can use real data. So as you can see in the demo, the comp value is increasing, which is the completed request. So once it hits 15, it generates the output, and it also gave you plenty of metrics while it was running and when it completed. So now this is just some snippets of that output. So it gives you timing, it gives you token values, word, input characters, output characters, request statistics, server throughput statistics, and as well as it lists out the outputs that it gave you, which currently are just the defaults. Here is a GuideLLM run config. So it is a more, rather than having to specify all of that in the command, you can specify most of it in a file, which is very useful for certain scenarios and also makes it much more easy to specify more complex scenarios. Like in this case, as you can see near the bottom, we run multiple sub benchmarks, starting with one stream and then going all the way to 300 streams. This helps you figure out how your server handles more and more load.
Now that we've got most of our background out of the way, let's dive into agentic workloads, which is the present and future of LLM benchmarking. If you don't mind, Jared, I lost slide controls, so could you just advance the slide? So on the left, you can see that diagram we had at the beginning of the slide deck. This is where LLM benchmarking began. We're looking at a single request, and we're looking at these events in the request. More common is this use case of having a conversation with the model. You send a request, the model responds back, you send another request, and you build this history chain of question and answers with the model. To do this, we need the tool needs to understand some concept of history and reintegrating requests with previous requests, this to give us a more realistic benchmark. And then next slide, please. However, today we've moved beyond that even. where we have this agentic system where there's some sort of orchestration layer that is handling not only talking to the LLM, but also maybe talking to sub-agent LLMs, which is maybe just another conversation, different chains of history, and even talking to tools and all of that reporting back to the harness. And could you advance the slide? Oh, there we go. So originally we had this like traditional benchmarking view where we're looking at it from the user's perspective, but that gives us limited insight into all these little individual events. So more recently, GuideLLM and other tools like it have been focusing on this system harness orchestration layer where we're looking at implementing all these features such as supporting dividing off to sub-agents, having a tree conversation style, tool calling, all of these other features. And Jared's going to go in depth in this section on all of these pieces and how we're supporting them in GuideLLM.
Multi-turn and tool and sub-agent support. So as we discussed earlier, multi-turn is basically when you are asking further questions to the LLM. It needs to have all the context of what you were talking about before, and therefore has to send back the full history every single turn, which does increase the load on the server. So it is important to model that accurately. We also need to support subagents. That has been a more recent feature, and it allows the main conversation to spawn additional conversations that basically do the work, do some other work, and then report back. They have independent histories, so therefore it's reducing the load on the server and having a more targeted context for that chat. In the diagram on the right, it's a visualization of a main conversation, which at turn 1 spawns 2 subagents that each run for 2 turns and report back just their last turn to turn 2 of the main conversation. We also support trace datasets, which allow replaying real recorded data rather than synthetic data. It has many advantages, including it is KV cache conscious by properly mimicking the cache hit rate and testing cache eviction timings. Trace datasets can support tool calling, subagents with dependencies, as discussed earlier, and the tools that run them, including GuideLLM, can support variable speed playback, and we also have plans for multiplication of those conversations for increased load. We already support Mooncake, and we have partial Weka support with full support coming for 0.8. And we have future plans for OTel, or Open Telemetry, which is another format that is being utilized for trace datasets.
All right, let's close out with kind of the current status of the GuideLLM project and some looking towards the future. So looking back at the past few releases, we've introduced a lot of changes to support new features. In the 0.5 or 0.4.0.5 timeline, we did a full architectural refactor of GuideLLM to allow us to extend it more, support some of these, support multimodal, I think was one of the main initial launch for that change, but also it let us scale tool better and everything. In 0.6, we focused on this like primitive version of multi-turn where it's just one request after another in chains. We added some in-process vLLM Python support, which we mentioned above, responses API, and various other things. And then in 0.7, which was our most recent completed release, we did a full rework of the CLI to better support like modular workloads, allow us to add features easier. We added some initial stuff for this replaying and tool calling, and also on the side, we ended up landing some audio transcription support, WebSocket audio transcription support. Looking towards the future, this upcoming release is mainly focused on that agentic tracing stuff you saw, supporting these predefined data sets like the Mooncake style data sets, the Weka style data sets, whatever. We'll also be doing a refresh of our HTML output. Anyone who's used that before knows it can be a little finicky, so we're completely reworking it so that it's much lighter weight and works a lot better. Additionally, we've seen some new backends land, like such as using the batch API for vLLM and benchmarking against that, or using LiteLLM as an SDK library. And then looking further forward in the Q4 2026 range, we're going to be looking at Omni support. We do support multimodal input, but we don't support output yet, so that's where that will be landing. Affecting our metric system to better support optional metrics, to let it make it easier to extend and maybe even add some like external metrics collectors, like the collecting off of the vLLM metrics. And then every tool these days, we have to have some Rust build or Rust integrated into it. This is mainly to allow us to scale the same way that vLLM is currently scaling with its new Rust front end.
So here is a preview of our in-progress prototype of the HTML output, which is just a simple self-contained HTML file that you can share, and it has a lot of visualizations to hopefully, and a lot of context so that both a technical and non-technical user can hopefully learn a lot from that benchmark. So what you can do to help, please tell us your use case. We are the developers, and if we can't live in a bubble and we need to know exactly what you need and if what we have created is working well for you. For example, the tool calling support was added recently, and we would love some feedback on if that specific implementation is good enough for your use case. And also, we are open source, so you can contribute. There's our GitHub link. Thank you. Any questions?
A lot in slides.
Yeah.
This might be a record. I think. Thank you guys so much for presenting, obviously, but also for everyone to doing the chat questions. I get so excited when there's so many questions. I don't even know where to get started. Michael, you usually run the Q&A. Do you want to emphasize some of these?
Yeah, there's a lot of complex topics here. I think like one that's good to just touch on is like how input data matters for inference performance.
Yeah, so it can depend a bit on your workload. Like if you're just doing simple Q&A and you don't have, say you have prefix caching disabled, then it really doesn't matter what you throw into the model for the most part, as long as you know how many tokens you want to throw in and how many tokens you want out, then that's fine. If you add prefix caching to the mix, you want to make sure that your data set isn't accidentally caching more or less than you would expect for your workload. So synthetic data helps us there because we can tune that cache hit rate with that kind of data. And then other things can complicate it, like if you're benchmarking a speculator model, you want to use data that's actually going to have a reasonable chance to correctly be guessed by the speculator model. You can't just use garbage because that'll end up with lower performance than you would actually expect in a real world use case. Then there's always like evaluation use cases where you have a data set you really want to run. And in that case, you use that data set, obviously.
Yeah, great points. I guess one kind of related, is there support for speculative decoding metrics in GuideLLM?
Not yet. We're working on it. Part of the complication there is that we just by default don't get anything out of vLLM from the API calls. So if we make a request to vLLM, we don't see any of those metrics coming back with that request. And so that was on the roadmap where we're looking at those metrics, endpoint scraping. And
yeah, I would just like to add towards that, Speculators ships an evaluate utility that uses GuideLLM under the hood to get speculative decoding metrics. So I've sent a link in the chat. Please check it out.
Okay, any other questions?
Yeah, this is a good time to unmute if anyone wants to ask them live.
Feel free to repeat your question in chat again. There was a lot of churn earlier, so we might have missed a few. Oh, go ahead.
Yeah, the speculative techniques are too many. P-EAGLE, MTP, T-Flash, DSpark, like multiple things. Like interesting. Which ones are suitable for what kind of attention mechanism? Is there any compatibility or matrix that's available in terms of giving a better latency and throughput?
So in Speculators, in the docs, we also ship a guide that can help you make that choice. But it really depends on your use case. In the sense, if your model already ships with a native MTP head, then we recommend trying to fine tune that. It's the easiest, trains pretty fast. If that does not meet your needs, then of course, DSpark is a more powerful algorithm. But yeah, I think that guide on Speculators, I'll just send the link in the chat, should be a good place to start.
Okay, thanks.
I want to follow up on this. So for different speculator algorithm, how much throughput or performance-wise differences? And comparing with how much benefit we can get from training DSpark or DFlash?
So MTP heads native. So it again depends on the model in the sense the MTP heads shipped with the Quen models are very good. So just fine tuning them gives you good performance. But the DSpark speculators that we've trained for Quen just do slightly better. And then again, every day we're trying to improve on them. So it really depends. I'm trying to find that link to the docs and I'll send it in the chat. It's a good place to start.
Great. Thanks.
Can I go ahead? Sorry. I had a question which Michael gave a response to regarding epochs versus training data trade-off. I think in the best practices talk that was in Speculators, it said you should ideally train for 20 epochs. And given something like perfect blend that becomes like 1.5 million, 1.2 million examples, do you have any best practices about how to think about how much training data you have and how many epochs you should train for broadly for DFlash specifically?
Yeah, I still, my opinion is certainly like what I shared in the chat. Yeah, like typically I think most of the time we train like 3 epochs on between 500K samples or 1.5 million samples. From my experience, you get the vast majority of improvement by epoch 1, but you can basically tell if it's going to be a good model or not by epoch 1, and then maybe you get another 20-30% quality by doing those extra 2 or 3 epochs. When you're training on a small amount of data, like 10K samples or 100K samples, we usually need more epochs and also like a different training setup to not deal with overfitting too hard. But yeah, I don't know. On my side, I mostly just try to train like general big DFlash or DSpark models. So generally like open perfect blend for 3 epochs. Yeah, okay. We can probably call it there because we're close to 10 minutes over time. So yeah, thanks everyone for coming to office hours. Thanks to our speakers for giving us a fully fledged series of talks. And yeah, if you want to get more involved with the community, join the vLLM Slack, slack.vlm.ai. You'll find many of these folks on there. Of course, get involved in the projects. Everything we talked about here is open source. GuideLLM, Speculators, Agentic API, and vLLM, of course. Get involved. Please let us know what features you care about that directly affects roadmap and what things we prioritize. And yeah, thanks for coming in after 2 weeks. And yeah, hope to see you again in another 2 weeks. So take care, everyone. Happy hacking.